Hello, my name is John, and today we're going to be talking about supercapacitors. To give you guys an idea of what a supercapacitor is, basically imagine that a battery and a normal capacitor got married and had a baby. That baby would be a supercapacitor. But seriously, that is the basic way to think of a supercapacitor. The way it's physically constructed, it has characteristics in common with both a battery and a normal capacitor. And the way it behaves, it has characteristics in common with both a battery and a normal capacitor. So to sort of give you guys an idea of how a supercapacitor behaves, let's take a look at the voltage behavior of each component. So first we'll do a battery. As can be seen, a battery has a sort of very constant voltage. It'll take many hours before that voltage goes down. Now we'll look at a capacitor. First, let me charge up the capacitor with the battery. Charging does not take very long. Then we check the voltage. And as you can see, the voltage shoots up and then decreases very quickly. And finally, we'll take a look at the supercapacitor. So the supercapacitor I've already charged. And if you take a look, the voltage holds constant, or at least it seems to hold constant, but this will discharge within a couple of minutes. It takes probably about 5 minutes. I have it charged up to about 2 volts right now. So it'll take about 2 minutes, 2 to 5 minutes to fully discharge. So as you can kind of see, the voltage characteristics between each one, battery constant takes many hours to discharge. Supercapacitor is about in the middle, takes minutes, and this one takes only a matter of seconds. So without further ado, we'll cue up the PowerPoint slides and get into the nitty-gritty details. So the technical name for a supercapacitor is an electrochemical double-layer capacitor. Energy storage is realized by a hybrid process that includes attributes from both the electrostatic capacitor and electrochemical battery. So to understand how this process works, let's look first at the basics of how a standard capacitors and batteries work. A capacitor is constructed by taking 2 conductive plates and separating by an insulating material called the dielectric. A voltage is applied across the plates, which causes a separation of charge between each plate. Once the separation of charge has been finished, an electric field is set up in the dielectric, which acts as the means of potential energy storage. If the capacitor is placed in a complete circuit, the negative charge carriers, which are mobile electrons, will move to the positively charged plate. Of course, net movement of charge is current flow. One last thing to note is that capacitors have fast charge and discharge rates. Later on, we will go into why discharge rates are different between capacitors, batteries, and supercapacitors. Next, let's see how a battery works. A battery is made of the main parts of an anode, a cathode, and electrolyte. The cathode and anode are immersed in the electrolyte, and a chemical reaction happens in the electrolyte that causes negative charges to come off of the cathode in a process called reduction. The negative charges then collect on the anode, and this is called oxidation. Due to the difference in charge between the anode and cathode, a potential difference is present between the two, causing a voltage. One thing important to note is that, as we've seen before, that our batteries have slow charge and discharge rates, and they store energy by electrochemical action. Next, let's look at a supercapacitor. A supercapacitor consists of electrodes, an electrolyte, and the separator, which prevents the facing electrodes from contacting each other. And in an electrochemical double-layer capacitor, an electrical condition called electrical double layer is formed between the electrodes and the electrolyte, as you can see here in yellow. And this basically works as the dielectric. So capacitance is proportional to the surface area of the electrical double layer. And now we typically activated carbon is used for the electrode, which has a large surface area, resulting in a very large capacitance values for supercapacitors. It's also important to notice that capacitance is also inversely proportional to D, and typically the distance D between the electrolyte and the electrode is on the order of something called angstroms, which have distances on the order of 10 to the negative 10 meters, so incredibly small distance. So the mechanism of ion absorption and desorption to the electrical double layer contributes to charging and discharging of the capacitor. When the supercap is discharged, the electrolyte is a soup of mixed charges. However, once we apply a voltage to the electrodes to charge the supercapacitor, the ions are drawn to the surface of the electrical double layer, and charge is complete with this nice arrangement of ions. When the supercap is discharged, the ions move away from the electrical double layer and bring the electrolyte to a more chaotic state in terms of ion distribution. And so there you have your sort of basic mechanism behind how supercapacitor works. Energy density is an important concept to understand when looking at the pros and cons of capacitors, batteries, and supercapacitors. And this wouldn't be a proper engineering-related project without some equations and mathematics. So let us analyze the energy storage and density limitations of a normal capacitor. Energy density is often measured in watt-hours per kilogram, with 1 watt-hour being equal to 3.6 times 10 to the 3 joules. Thus, the energy capacity of a device is normalized to its mass. For batteries, the energy density extends between about 30 watt-hours per kilogram for a lead-acid battery to as high as 150 watt-hours per kilogram for a lithium-ion battery. In contrast, the energy density rarely exceeds 0.02 watt-hours per kilogram for a traditional capacitor. Let us examine the limits of the value of the energy density for a capacitor by considering a small parallel plate capacitor with plate area A and separation between plates D. For simplicity, we will assign the capacitor a voltage rating of 1 volt, the maximum anticipated voltage across the capacitor. Our goal is to maximize the energy density, W prime. For a parallel plate capacitor, the capacitance is equal to epsilon times A divided by the distance, where A is the area, D is the distance, and epsilon is the permittivity of the insulating material. We will also use the equation for energy at a capacitor. The energy W is equal to 1/2 the capacitance times the voltage squared. So using our equation for energy density, which is the amount of energy per unit of mass, where M is the mass of the conducting plates and the insulating material contained in the capacitor. To keep this simple, we will assume that the plates can be made so thin as to ignore their masses relative to the mass of the insulating material. If the material's density is rho in units of kilograms per meters cubed, then the mass would be equal to rho times the area times distance. And then our energy density W prime would be equal to epsilon times voltage squared divided by 2 times rho times the distance squared. To maximize W prime, we need to select D to be the smallest possible, but we also have to be aware of the constraint associated with dielectric breakdown. To avoid sparking between the capacitor's two plates, the electric field strength should not exceed a value called EDS, the dielectric strength of the insulating material. Among the various types of materials commonly used in capacitors, mica has one of the highest rating values of EDS, nearly 2 times 10 to the 8 volts per meter. Breakdown voltage, VBR, is related to EDS by VBR is equal to EDS times D. So given that the capacitor is to have a voltage rating of 1 volt, let us choose VBR to be 2 volts, thereby allowing about a 50% safety margin. With VBR equal to 2 volts, and EDS equal to 2 times 10 to the 8 volts per meter, it follows that the distance D should not be smaller than 10 to the negative 8 meters, or 10 nanometers. For mica, epsilon is equal to about 6 times epsilon naught, and the density is about 3 times 10 to the 3 kilograms per meters cubed. Ignoring for the moment the practical issues associated with building a capacitor with a spacing of only 10 nanometers between conductors, the expression for energy density leads to W prime being about 90 joules per kilogram. Converting W prime to watts per kilogram by dividing by 3.6 times 10 to the 3 joules per watt hour gives an energy density maximum of about 2.5 times 10 to the negative 2 watt hours per kilogram for a traditional capacitor rated at a voltage of 1 volt. So our basic conclusions from this are that the energy storage of capacity of a traditional capacitor is about 4 orders of magnitude smaller than the energy density of a lithium-ion battery. Figure 1.5 shows typical values for attributes used to characterize the performance of electrical energy storage devices. This includes power density, charge and discharge rates, and the number of charge-discharge cycles the device can handle before performance goes down. An approximation of discharge rate is the energy density divided by the power density. So as we can see here on the graph, we know traditional capacitors have really slow charge and discharge rates. I'm sorry, very fast charge and discharge rates. And this is due to the fact that they have a very small energy density but a really high power density. You can also see that batteries, which have very slow charge and discharge rates, have a large energy density but a small power density. And then here, of course, supercapacitors have a high power density but only sort of a medium energy density, which is why their charge and discharge rate is in the middle between batteries and capacitors. Also, that can be seen on this graph is that supercapacitors can store hundreds of times more energy than a regular capacitor. As you can see, the scale is on magnitudes of 10, but it's slightly less than a battery. However, supercapacitors can discharge their stored energy in only a few seconds, compared to the hours it would take a battery to discharge the same amount of energy. One more advantage that a supercapacitor has over batteries is that its cycle life is thousands of times greater than a battery. Due to these features, the supercapacitor has increased the use of capacitors in electric systems. Up here in the upper right corner of the graph, you can see future developments. This is where the holy grail of energy storage sits. Hopefully one day in the future, we can reach this area and have easy, light, and compact energy storage for all of our power needs. Next, let's take a look at applications. First, we're going to go to the data sheet. This is the data sheet for the capacitor that you guys saw earlier. Some applications given are for high shock and vibration environments, automotive subsystems like electric vehicles, wind turbine pitch control, hybrid vehicles, rails, heavy industrial equipment, and UPS and telecom systems. Another thing I wanted you guys to see is the capacitance rating for this capacitor that I have has a maximum capacitance of 780 farads, which is absolutely massive. Typical capacitors only have capacitance ratings of something on the order of microfarads. So a supercapacitor literally is a supercapacitor. It has capacitance rating millions of times greater than a normal capacitor. One other sort of new developments as far as the applications is that there's also been research done for photovoltaic systems where supercapacitors could potentially replace the large expensive battery banks used for energy storage. And the link for that research is right here. Thank you for watching. I hope you all have a better understanding of how a supercapacitor works.